Hello, Professor. I have finished my test corrections and I believe I understand the material now, so I will begin. So, started off number 1A, incorrect, unfortunately. In a regression problem, the target variable is discrete. The reason this is actually false is in a regression problem, the target variable can be continuous or discrete. So for 2B, which of the following is true about the rank of a matrix? I'm not really sure why I marked D, because I'm pretty sure I had in my notes linearly independent instead of dependent, but that's pretty straightforward. That's just the basic definition of rank of matrix that's how it's calculated, is by the number of linearly independent columns, which that makes sense because you wouldn't want multiple sets of linearly dependent columns in the matrix in most cases. For D, I marked all of them true. So for A, the binomial distribution is continuous. Probability distribution, this is actually false. I was thinking of it as like 0.5 and 0.5, 0.49 to 0.51. I think that would be a continuous selection if that's what we were talking about, but we're actually referring to the success or failure here, so that's why I believe it's a discrete distribution as opposed to continuous, so that's why A is false. B is still true. That's just the basic definition of binomial distribution is n times p. And therefore it would follow that for C would be false because the variance of a binomial distribution would be np times 1 minus p. So same thing, straightforward definition. I shouldn't have got that wrong. Well, obviously I did get that wrong. I'm saying I shouldn't have marked C as true. D, the binomial distribution is a distribution of the number of successes to a sequence of independent experiments. This is also true. I had originally marked that as true, and actually that's really the basic definition, and B is actually the definition of the expectation, of course. So moving along. So for E, which of the following statements are true? K and N classifiers. A, the classification accuracy is better with larger values of K. That can actually be false in many cases. The bias can increase with larger values of K, and I believe that's the reason that that's not one of the correct answers. So for B, the the decision boundary is smoother with larger values of K. This is of course true. The decision boundary does become smoother with larger values of K, and that's because it's typically smoother when K has more neighbors. So KNN is a type of instance-based learning. This is true. The classifier is trained on instances to provide the predictions. So for the next one, F, which of the following is true about the effect of increasing K and K and N? Kind of already been through A and B. A and B are, well, A is not true. You may have more bias as you increase K. And B is true. The decision boundary is going to be smoother as there's more neighbors for K. or as k, I should say. And for C, the higher the value of k, the higher bias in the model. That ties into my explanation for A. So I would say that is true. And for D, the higher the value of k, the higher variance in the model. I believe the reason we're saying there is more bias in a higher value of k is because we're saying that a higher value of k is going to lead to less variance. So naturally D would be false. So for G, when you provide more examples for training, the bias of your model trained on will... So when I look for answers for this online, there's a lot of conflicting information and not a lot of consensus. But I believe the answer we're looking for here is increase. And I believe the answer for that, like I just mentioned, is when you provide more examples for the training, you may decrease the variance. And if you decrease the variance, you are increasing the bias. So I believe that's our line of thinking there. So for I, I'm having difficulty understanding why this is incorrect. Of course, we're being asked which of these hyperparameters, when increased, may cause random forest to overfit the data. And based on my notes from before the exam and my research afterwards, it seems like all three of these can easily contribute to overfitting when they're increased. So I think our line of thinking with the number of trees is similar to the previous question, where we may overfit the data by decreasing variance by increasing number of trees. Okay, please forgive me. While trying to explain why my answer was right, I understood why it was wrong. Just needed to pay a little more attention to the actual question being asked. And the question is not which of the following hyperparameters increase overfitting. The question is which of the following hyperparameters pertaining to random forests can cause overfitting when increased. So I believe the answer would be all three of them, or D, 1 and 2, if it was pertaining to not just random forests. But now with random forests, it makes sense that 1 and 3 would not cause overfitting. I guess the same problems of bias and decrease in variance don't apply for random forest, so maybe that concern is alleviated. And but you would still need to be concerned about the depth of the tree, because it could get obviously stuck in the depth of the tree and get very long and complex to where there could be a lot of noise from that tree, and that could obviously cause overfitting. So the answer for that is actually B. I lost a few points on my recall calculation here, so I'll go ahead and write that out. So we have TP, AP, and if I had just calculated it this way, obviously, I would have gotten the right answer. I don't know why I made that an I. There we go. So how many true positives do we have? We have 80. How many actual positives do we have? We have 100. We're trying to understand how our rate of true positives compares to our rate of actual positives. And the way we do that is true positive over actual positive. So in this case, we're going to have 80 over 100. It's going to be 4 over 5. So that was my incorrect calculation. All right, so we've also got to calculate average precision. Again, I just got to pay attention to detail. We're asking average precision. We're not asking for the same thing that we asked in the question above, which was just a direct comparison to precision at a certain point. Instead, we're asking the average precision. So in this case, okay, so let's do model 1. So relevant is 1 over 1, 1. Then we've got 1 over 2, 2 over 3, 3 over 4, 3 over 5, 4 over 6, and 4 over 7. Okay. And then put a little M1 next to that. So then let's do M2. First guy's relevant, so we're 1 over 1 plus another 1 because we're 2 over 2 plus now we're 2 for 3, 3 over 4, 3 over 5, 4 over 6 is 2 over 3, and 5 over 7. So just based on that, well, I've already calculated this once before, so I know, but this just looks like the second one's going to be bigger, although you're just asking for the actual calculation, not which one's more. So good old Casio, you can see the buttons are nice and faded, all the years of use. 1 over 2, 2 over 3, 3 over 4, 3 over 5, 4 over 6, or 2 over 3, and 4 over 7. Okay, I actually got 4.75. Or that's what I love about this calculator is this little button that you can't even see what it used to say, but changes gives you the notation. I was born in 1997, so I like that number. So we are 1997 over 420. .75. Let's do the same thing again. 1 plus 1 is 2, hoping that still holds. 2 over 3. 3 over 4. 3 over 5. Another 2 over 3. And a 5 over 7. So that says 2267 over 420. It's funny that they're both over 420. 5.39. I'm almost certain that's what I got last time. Yeah. So Bayesian. This is pretty much what I had on my paper before. Maybe I was just a little sloppy with the notation. But as far as I can see, so starting with the first one, probability of hypothesis given evidence. This is also called the posterior. I called it the expectation here. And that's what we're trying to calculate in the overall. That's what we're using Bayes' theorem to calculate. So we have the probability of E given H, which is the likelihood, and we're saying it's the probability of the expected given the hypothesis. P of H is just the probability of hypothesis. So this is the prior probability. P of E, probability of evidence. And we can also call this the proof. So I guess to go in more detail, we could say that the P of E is the probability of observing event E, or evidence E. So hopefully that is a sufficient explanation of those terms. All right, thank you very much, Professor.